Hello and welcome to GCSE Chemistry Paper 1 Revision Part 1 with me, Mr. Duffy. This is Part 1 of a 2-video series, and in Video 1 we're going to be looking at the absolute basics, Topic 1, atoms in the periodic table, Topic 2, structure and bonding. These are the absolute essentials all students need to know, and then these will build a strong foundation for you to get onto the higher grades, okay? To get the lower grades, you really need to know the first two topics, topic 1 and 2, and then video 2 will move on to topic 3, which is mainly moles, topic 4, your acids and metals, electrolysis, and then topic 5, your kind of exo and endothermic reactions. Now I'll just get rid of my face so you can see the screen properly, okay? Getting those next three topics will move your grade boundaries to the left into the higher grades, but you need a solid foundation first of all. So why 2 videos instead of 1? Well, what's the point of these videos? 1, to help you to understand the content, and secondly, 2, to help you to know what to actually write in your exam to get the marks. Just because you think you know something does not mean you'll get the marks in your exam for writing it if you do not hit what's on the marking scheme. So what you're going to find is this video is very exam focused. There are plenty of videos that say exam revision in 45 minutes. It is impossible to revise 49 chapters to exam standard in under an hour. That's why I split it up into 2 videos. It's just not possible. You also have people who, with crystal balls, are predicting what's going to be the future. No one can predict the future, okay? So I am not leaving anything to chance, and I will cover every corner of the course. I will not make any predictions. I'm going to cover everything. It's better safe than sorry. So this is exam focused. You're going to see lots of past questions, marking schemes, clear step-by-step answers, model answers, and from a teacher, myself, who's got over 15 years experience teaching this course. Also, the slides are designed for mobile phones, okay? I designed them specifically for this because instead of watching TikTok, you could maybe use your phone to study. These videos are particularly designed for mobile phones. They got large slides and large text. I love science, and I find it mind-blowing, and I would maybe hope that you go on for a career in science, but even if you don't want to, this video will definitely help you with exam success. So how to use these videos, okay? One thing to be aware of is something I call cognitive overload. That is when your brain can't take too much information at once, okay? It's just too much. So you're going to be using the play and pause button pretty regularly throughout this video to help you digest the information because it's too much to take in one go. If you don't get something, just repeat and rewind it and look at that clip again and again and again, and it might get in the 3rd time, and if not the 3rd time, maybe the 5th time. That's the beauty of videos. You can just keep on doing that. If you're a bit freaked out saying that you've left your revision too late, well, don't worry. I'm still sending you good vibes, and if you watch this video, and if it's even on the day of your exam watching this video, the very best of luck. Anyway, let's get started, okay? If you do okay, let's go. All right, let's go. AQA Chemistry Paper 1 topic list, okay? Here's the triple topic list for 1 and 2, and here's you might want to pause to have a quick look at this. Just atoms in the periodic table. And here is the combined topic list, okay? They've got rid of transition metals, but it's pretty much the same otherwise than that. And they got rid of nanoparticles, but it's pretty much the same apart from that, okay? Now, I really want you to get used to scientific notation. You need to be able to work with these numbers and know what they mean, okay? For example, nano means billionth, micro means millionth, and so on. And you need to know the big numbers as well, like mega means million, giga means billion, and tera means trillion. You need to know these numbers. Okay, on to topic 1, atoms and the periodic table. Here's the topic list. Let's get started on atoms, okay? If there was a nuclear holocaust or something and the whole world ended, a group of scientists sat down and go, what's the most important piece of information to pass on to people trying to rebuild? They came up with this. Everything is made of atoms is the most important sentence in all of science. Well, if it's the most important sentence, you should know about it, okay? So you should be aware of this basic picture by now of a central nucleus with protons and neutrons and electrons orbiting outside. The first thing to take from the slide is what's highlighted on the left, the dimensions. An atom is 0.1 nanometers and the nucleus is 10,000 times smaller, 0.0001 nanometers, okay? Now, there are some mistakes in this diagram. As I said, the nucleus is way smaller than is displayed. It's swollen up so you can see it. Protons and neutrons are way more massive than the tiny electrons. In that diagram, they were the same size. They're actually nearly 2,000 times more massive. And finally, there's no such thing as actual color. They're not actually blue, red, or green down at that level. Okay, you might want to play and pause while I go through this table that sums everything up. Okay, moving on. Let's talk about electrostatic forces because this is crucial to our thing, okay? Things that have like charges repel, like two positive charges repel or negative. Opposite charges attract. You're going to see this is very important later on, particularly when we talk about ionic bonding. Now, this is a commonly asked question, identifying the particle. Well, if opposite charges attract, the red electron was attracted to the positively charged plate. The neutrons fly through the plates because they don't feel any charge, and the proton will be attracted to the negatively charged plate at the bottom. This is a commonly asked question. There are over 100 different types of atoms. See the periodic table. Everything in the universe is made from atoms, including you, and an element is a substance made from just one type of atom. And here are some elements: gold, copper, carbon, oxygen. They're all elements. And the periodic table, this is the one that will be given to your exam, gives you all the information you need to know about these. A compound is a substance made from two or more elements chemically combined. Here's the example of sodium chloride, one sodium joining with one chlorine to make salt. And the thing I love about chemistry is sodium is like a soft reactive tinfoil metal. Chlorine is a real toxic gas. If I breathed it in, it would kill me. But when you mix them together, you get a white crystalline thing you can safely sprinkle on your chips. Here are some other simple compounds. You want to pause for a second, have a quick look at them. Now on to an atom. The key point about this slide is all atoms have a charge of 0 because they have the same number of protons and electrons. Here's lithium, 3 protons, 3 electrons. If it's iron, 26 protons, 26 electrons. If it's uranium, 92 protons, 92 electrons. It always adds up to 0. Okay, now here's the largest element that we have discovered so far, organocin. Okay, it's got 118 electrons, and we're going to talk about that in a moment, but you need to be able to find the number of neutrons. The bottom number is the atomic number, the number of protons. The top number is the mass number, the number of protons and neutrons. You subtract the bottom number from the top number to get the number of neutrons. Magnesium has 12 neutrons. Let's take a look at this organocin. There's only ever made 5 or 6 atoms of the thing. That's all they've ever made. But 294 minus 118 is 176 neutrons. You need to be able to find that number of neutrons. Typical exam questions. Here's where you might want to play or pause as I go through them. Here's a nice simple foundation level question here. And here is the same question again about the direction. The electron attracted upwards, the proton attracted downwards, and the neutron feeling no charge. And now here's a 6-mark question, and this was actually answered terribly because students weren't prepared for it. Describe the structure of an atom. So pay attention to these, please. So that's the perfect 6-mark answer. You should learn that as we go along. Moving on to isotopes. So what are isotopes? Isotopes have the same number of protons but a different number of neutrons. You can also say they have the same atomic number but a different mass number. For example, here's carbon 12, 6 protons, 6 neutrons. Carbon 13 has 1 extra neutron. Carbon 14 has 2 extra neutrons and is actually radioactive, and it's actually used to date really old things like that old skeleton there. Here's some isotopes of hydrogen. And here's some isotopes of uranium, okay? And uranium-235 is a particularly important one you're going to see in physics as it can be involved in nuclear fission, okay? Uranium-238 is non-fissionable. Uranium-235 you can make nuclear bombs out of. Now, here's a commonly asked question. Why are there decimals in the periodic table? It kind of implies that there's half a neutron, and there isn't half a neutron. So what's going on with chlorine and copper? I'm going to take a look at chlorine in detail now. How can it be? How can it be? Well, the fact is there are two main isotopes of chlorine, chlorine 35 and chlorine 37. And the fact is there's just 25% of chlorine is chlorine 37, and 1 in 4, it's just too big a percentage to ignore. So you have to be able to do this calculation here. 75 times 35 plus 25 times 37 all over 100 gives you 35.5, and you should practice doing that calculation yourself. Here's another player pause moment. See where I got the numbers. This element would actually be magnesium. And I want you to practice these yourself to make sure you get the same answer as me. And beware of significant figures, rounding up to 0.2. So every element has lots of different isotopes, but we only include 2 in the GCSE periodic table. Here's a more realistic periodic table. Next on is balancing equations, okay? And it's all about the law of conservation of mass, okay? In a chemical reaction, atoms are not created or destroyed, they are just rearranged. So the mass of the reactants equals the mass of the products. Here you can see 80 grams of reactants, 80 grams of products. So for example, if you take a look at the top one, what's the missing figure? Well, there's 50 on the left, so it should be 35 to make 50 on the right, or 50 on the left. And then there is 340 on the left. It should be 200 to make 340 on the right. Okay, moving on, the top chemical equation is unbalanced because there's only one oxygen on the right. When I put 2 in front of it, okay, this now is a balanced chemical equation. If you do notice that one of the mass is not the same in the products, it's generally because some mass is lost as the gas. They like to ask that question if the mass of the products is not equal to the mass of the reactants. Balancing equations, well, how do you go about it? Okay, I'm going to talk about the combustion of propane, which is the gas they use in barbecues. Okay, here is the equation for combustion of propane in oxygen. And as you can see, it's unbalanced. We're going to balance it now. And it's all about trial and error. There's no shortcut to balancing chemical equations. You just have to keep at it. So, I notice firstly there's 3 carbons on the left, but 1 on the right. I'm going to start dealing with that. I put a 3 in front of the CO2. Now the carbons match. The hydrogens and oxygens still don't match. I'm going to deal with the hydrogens next. Well, if I put a 4 here, 4 times 2 is 8. I now have the carbons matching and the hydrogens matching. I have 10 oxygens on the right. If I can get 10 on the left, I'm done. Well, 5 times 2 is 10. This is a balanced chemical equation, successfully balanced. Okay? Now, I want you to not spend too much time in this. Students come out of exams all the time going, I couldn't balance the equation. It took me 10 minutes. I couldn't balance it. It's worth 1 mark to balance an equation. You get 1 mark for getting the reactants, 1 for the products, and only 1 mark for balancing. So don't waste too much time on it, please. I have exam technique tips at the end of the second video, and I really need you to see them as well. So here's an example where you just get 1 mark for the balancing. Okay, next up, mixtures versus compounds. The classic example is iron and sulfur. When I mix iron and sulfur together, I can separate them because iron is magnetic and sulfur is not magnetic. That is a clear example of a mixture. But when I heat them together, I make a compound called iron sulfide. Iron sulfide is no longer magnetic and can't be separated. Okay, so that is an example of a mixture versus a compound. And the key point is this: mixtures can contain variable ratios. That means I could add a bit more sulfur, a bit more iron, it doesn't matter. but a compound always has the same ratio of atoms, and in the case above, it will always be 53% aluminium and aluminium oxide. They have a fixed ratio. And speaking of ratios, you now need to be able to find the empirical formula. Sorry for the little buzz there, this is a change of period. Okay, just looking at these ratios, you can see that it's a 1 to 1 for sodium chloride, 1 to 2 for magnesium chloride, 1 to 3 for aluminium chloride, and then a 2 to 3 ratio for aluminium oxide, which is a huge part of our course. So you should play and pause while I go through how we find the empirical formula of a compound. So what is the empirical formula of magnesium chloride if 0.96 grams of magnesium combines with 2.84 grams of chlorine? And I've given you the molecular masses to save you time. Step 1, divide the masses by the molecular masses of the compound. And I've done that, as you can see, and I get 0.04 and 0.08. You then divide by the smallest answer, which is 0.04. And on the left hand side I get 1, and on the right hand side I get 2. That gives me the empirical formula MgCl2. You can also do this question with percentages, and here's a 5-mark question, so it is going to be a bit more difficult, but it's, as you can follow the numbers, it's not that hard, okay? It's going to be 22.8 divided by 23, 21.8 divided by 11, and 55.4 divided by 16. Now when I do the last one, I get 3.5. You cannot have a decimal. If you end up with a decimal, you have to multiply everything by 2. You have to double everything up. So 1 times 2 is 2, 2 times 2 is 4, and 3.5 times 2 is 7, which gives you the overall formula Na2B4O7. That's why it was a 5-mark question, because you have to double everything up. Next we're up to how do we separate mixtures. The first one is chromatography, separating mixtures of colors. Now this is more paper 2, topic 8, but you do need to know the basics in topic 1, okay? So as we can see, there are a solvent, that is the mobile phase, and the stationary phase is the paper. And the water just basically will drag up and spread out the ink as it soaks up through the paper. Now, so the phases, mobile is the solvent, usually water, that moves up. Stationary is the paper, okay? Now you might want to play and pause as I talk, as you can see the exact mechanisms here. Why do the different colors separate? Okay, well they will have different solubilities in the solvent. The more soluble dyes will travel up further with the solvent, the less soluble dyes will not travel up as far, and some will just stay right at the start, they're not soluble at all. Secondly, they have different affinities for the paper itself. If they have a higher affinity, they'll stay stuck near the bottom. If they have a lower affinity, that means attraction, they will travel further up. And here's a real life exam question, if you want to pause and have a quick look at that. Next, you need to know these state symbols. Everyone knows SL and G. AQ means aqueous, a solid dissolved in water. So if I have pure water and I put salt into it, it's NaClAQ because it's salt water. Now, how do you separate a soluble solid from a solvent? You heat it up, okay? The solvent, the water, will evaporate, and the solute, probably the salt, will be left behind. That's how you separate them. They often use sunlight to do this in countries. You're going to see this in topic 10 in chemistry, to get rid of the salt water before they clean it for drinking. Next, separating an insoluble solid, that's S, something that doesn't dissolve. This is really easy. You just use filter paper in the funnel. The water is really small and pass through the gaps in the filter paper, whereas the large insoluble molecules will stay stuck in the filter paper. Separating mixtures of liquids, well, that's called distillation. You're going to see more of that in like fractional distillation of crude oil. But for now, I'm separating water with alcohol. They have 2 different boiling points. So the alcohol should boil off first, and you can see separating it out at the bottom right there. Distillation, separating liquids because they have different boiling points. This leads on to experiment 1, making salts, and you need to put some of these techniques together, okay? You've all probably done this, looking at the bottom left, making copper sulfate. So, Experimental write-ups. What are the key? You must say what are you are measuring and how you are measuring it. Even if you don't have a clue about the experiment, just say something like we measure the temperature with a thermometer, you'll get a mark. We measure the time, no marks. We measure the time with a stopwatch, you get the mark. We measure the mass, no marks. We measure the mass with a balance, you get the mark. We measure the volume with a measuring cylinder. Even if you don't know what's going on, say stuff like that and at least get a couple of marks rather than zero. So here's some quick pictures of the crucial devices. And now here's the actual write-up, okay? An acid and an alkali give me a salt and water. It's a neutralization reaction. And here's my desired product, copper sulfate. You might want to pause for a second to quick look at the diagram. And then here it's the write-up, okay? Pause, read it, take your time, and you might repeat and go over this a couple of times. This is the 6-mark write-up. Now, you must always put a bit of safety in your write-up as well. For example, you're dealing with near boiling acid, so you'd be wearing safety goggles. The beaker is probably very hot, so you'd use the tongs. Always include a bit of safety in your write-up and you'll get an extra mark as well. Now, some questions about this experiment. Why do you use excess copper oxide to ensure all the sulfuric acid reacts? Why can you filter the copper oxide? Copper oxide is insoluble. The blue copper sulfate liquid is soluble. It will pass through the filter paper. And finally, why is the acid heated? It increases the rate of reaction, ensures all the sulfuric acid reacts. So here's another picture of filtering the copper oxide. You can see it is too big to pass through the gaps in the filter paper. Now, why can't I do this? Why can't I just use the liquid, use a Bunsen burner? Well, it's about crystallization, and crystallization takes time. So you leave them maybe over the weekend so the crystals can grow. If I evaporate the liquid straight away, I wouldn't get any nice crystals like this. So that's why we don't actually use the Bunsen burner technique. You need to be able to apply this to any neutralization reaction to make any salt, and it'll be the same technique. Next, on to the structure of an atom and how we have discovered it. Okay, so discovering the structure of an atom. Firstly, the atoms come from the words Greek atomos, meaning indivisible. We now know atoms are divisible, but it is struck. And they thought atoms were these indivisible little spheres. That stayed up for a long time until the 19th and early 20th century, where they actually figured out what was going on. So in 1897, electrons were discovered, and they were found to be in everything. So everything contained electrons, and here's the experiment he did to find that out. But if electrons are in everything and like charges repel each other, then what's going on? Not everything in the world is repelling each other. The world is neutral. So there must be a positive charge to cancel out the negative charge. And the real question was, where is the positive charge in the atom to cancel out the negative charge? Where is it? Well, there was 2 models proposed. There was the plum pudding model, and what you say it is electrons embedded in a sphere of positive charge. And on the right you have the nuclear model, which is a tiny positive nucleus with electrons orbiting outside. So, on a side note, I have to talk about radioactivity. I thought this was chemistry, not physics. Why you talk about radioactivity? Well, here's why, okay? Well, here's the 3 people who won the Nobel Prize in physics. Becquerel, who the unit is named after. Marie Curie, probably the most famous female scientist of all time. She won 2 Nobel Prizes. And her husband, Pierre Curie. Well, they just didn't know about radioactivity, okay? They put it in water, they put it in butter, they put it in toothpaste, and your man Becquerel died 3 years later, but probably of radioactive contamination. Marie Curie died, she lasted a few more years, but she died of cancer too, due to exposure. And as for her husband Pierre, well, he was actually just run over by a horse in 1906. But if he had lived longer, he probably would have got cancer too. Anyway, why am I talking about radioactivity? Because it's all about the alpha particle. An alpha particle is a positively charged helium nucleus, which leads us on to the famous alpha scattering experiment. And this is what was used to distinguish between the plum pudding and the nuclear model. So let's take a look here. So the thing is, atoms are too small to see. We can't see them, so we have to use indirect methods, okay? So Ernest Rutherford came up with the idea, why not fire a load of alpha particles at a thin sheet of gold and see what happens, see if we can get any information. Just a quick aside, if alpha particles are stopped by paper, how do they pass through gold? Well, gold is really malleable, and they made it 2,500 times thinner than paper, so the alpha particles can pass through. It's called the gold leaf experiment sometimes, because it's so thin. Now, on the left you have the plum pudding model, and on the right you have the nuclear model, okay? And here is the key point, okay, is the deflection of the particles. Alpha particles travel very fast, 20,000 kilometers a second. They can go around the world in 2 seconds. Now, in reality, they only travel a few centimeters before they're stopped, but they do travel with a lot of energy. Now, for an alpha particle to bounce off and be reflected, it means there must be a very small, dense nucleus. So here are the three lads who did the experiment, and you might want to play and pause while we read through what they were talking about. So the main thing is they made hundreds of thousands of measurements, which made it reliable, and he found that basically some alpha particles were deflected or reflected, and he thought it was like the equivalent of firing a cannon at a piece of tissue and the cannonball coming back to hit you. It was just incredible. So, what is this? They ask this all the time, and you might want to just make sure you really play and pause and get this into your head. Observation 1. Most of the alpha particles pass straight through the gold. Conclusion 1. Atoms are mostly empty space. Observation 2. Some alpha particles were deflected or even reflected. Conclusion 2. Most of an atom's mass is concentrated in a tiny positive nucleus. This is absolutely essential stuff. Now, compare the plum pudding model with the nuclear model. You might want to read this. Again, using play and pause. And people are good at differences, not so good at similarities. Neither model has neutrons. Is a similarity in the marking scheme. You should include that. And now, this is a common mistake. This thinker gave this picture of the atom. It did not give this picture of the atom. The only picture of the atom after the alpha scattering experiment was this. A positive nucleus with electrons orbiting outside. Do not say the electrons are in shells. That's next. Do not say the nucleus had neutrons. The neutron wasn't discovered until 1932, and the proton not till after 1917. Just a positive nucleus, that's it. This is kind of more like what they're talking about. Now, the next person on our list is the Bohr, Niels Bohr, okay? And he came up with the idea of electron shells, where they, instead of orbiting in any way, they orbit in shells. 2 in the first shell, then 8 after that. Okay, you should know that basic rule by now. So here's hydrogen at 1, helium at 2, full, new shell, lithium 1, beryllium 2, and then so on and so forth, until with neon it's full, then you have a new shell, then argon it's full and a new shell, and so on and so on. That's the arrangement of electrons. You need to be able to write the electronic structures as follows, where each dot represents a new shell. Look at lithium 2.1, sodium 2.81, and potassium 2.881. They're all in group 1. And the final piece of the puzzle was when neutrons were discovered in 1932. That was a major discovery because people were finally knew what isotopes were. Isotopes have the same number of protons but a different number of neutrons. You can't know that definition if you don't know neutrons didn't exist. Here's the experiment he did, but you don't need to know it for your course. Now, and this finally left us with the picture of an atom with a positive nucleus of protons and neutrons with electrons orbiting in shells. Now, here are some commonly asked questions, okay? So, here's the alpha particle one. Now, each answer may be used more than once. Well, if they say that they want you to use each answer more than once, this question was answered terribly, okay? If they didn't say that for no reason. So you can see increases is used twice. The results were replaced, explain why it's a general scientific question. Okay, the results could not be explained by the plum pudding model. And finally, why did scientists believe it? They made so many measurements. They made over 100,000 measurements and they were respected science. This was general science questions. So that is topic 1A done. Now we're on to topic 1B, the periodic table and groups. Okay, so we'll fly through this now. So here's the modern periodic table, which is range and order of atomic number, the number of protons. We're going to see how we got it there, but we start off in the mid-19th century. They didn't know about the nucleus, they didn't know about electrons, no protons, no neutrons, not even the concept of atoms was fully believed by scientists. So, here's the first attempt by this guy called Newland, this law of octaves, where every eighth element was similar. There was a lot of mistakes, and it was arranged in order of atomic weight. You can see some mistakes in this table straight away, okay? Hydrogen is in group 1 with the other halogens, that's wrong. Iron is in group 7, and you can see in the last with oxygen and sulfur, they're non-metals. And finally, there's no group 0, no noble gases, they weren't discovered yet. Here's a fuller version of his table, and as you can see, he's even put some 2 elements in the same box, okay? He's kind of was into music, and he thought it would be like an octave of music, completely wrong. So, Newland's periodic table was not widely accepted. Here's why. Some boxes contain 2 elements, the columns contain different elements with different properties, and he wasn't actually that well known a scientist. On to our hero, Dmitry Mendeleev, a Russian chemist, and he came up with the foundation of the modern periodic table. He left gaps. He realized that not every element had been discovered yet, and he left gaps for them. Okay? He predicted the properties of these elements, and when they were discovered, their properties closely matched his predictions, proving him correct. That's how science works. You predict something, they do an experiment, and if it matches your predictions, you're correct. What kind of stuff did he predict? He predicted whether they be metals or non-metals, their atomic mass. Don't say atomic number because protons weren't discovered. Melting and boiling points and densities. I'm going to give you an example of silicon and what he called ecosilicon, which will be the element below silicon. Okay, it was discovered in 1886, and believe it or not, it was discovered in Germany. And let's match the properties of silicon and the element directly below it. He predicted their properties 72, 72.59. The densities are very close, high melting point. His predictions were spot on pretty much, and that gave strong support. He also did this, if you look at the bottom right, tellurium and iodine, okay? He basically, if he went by atomic weight, then tellurium should be in with the halogens and iodine shouldn't. But he decided that it was more important to have this element with the same chemical properties, so he swapped iodine and tellurium around. Once we know about protons, neutrons, and electrons, this made sense, but he just did it because of the chemical properties. Remember, they didn't know any of this stuff. Once we did discover this stuff, we got the modern periodic table, and we've already been through that. Now, you might want to play and pause while we go through some exam questions. Okay, a 6-mark question comparing Newland and Mendeleev's table. That's a tough question to get. Let's have a quick look, okay? Newland's table had many elements with dissimilar properties. Mendeleev's did not. Newland's table did not leave gaps for undiscovered elements. Mendeleev's did. When these undiscovered elements were discovered, their properties closely matched his predictions. That's the key point. Now here's where students struggle is similarities. Both tables were arranged in order of atomic weight, and neither table had the noble gases because they just weren't discovered yet. Now next, why do atoms react with each other at all? So here's the periodic table, but if none of these elements stuck together, there'd be no life, there'd be no Earth, there'd be nothing, okay? It'd be a very boring universe if chemical reactions didn't happen. So why do atoms react? All atoms want a full outer shell. Why? It is the most stable configuration and it is the basis of reactivity. Atoms will gain, lose, or share electrons to have a full outer shell. Now we need to talk about the groups, and there's three groups in particular: group 1s, group 7s, and group 0. All group 1s lose electrons of a charge of +1. All group 2s lose 2 electrons of a charge of +2. Transition metals will be positive, but we can't say for sure, so they don't have a set group. All group 3s form positive ions. And then on the right hand side of the periodic table, they gain electrons to become negatively charged. Finally, with group 0, it's not called group 8 because of helium. It only needs 2 electrons to have a full outer shell, so it's called group 0, the noble gases. Right, group 1, the alkali metals. They are low density. They'll float on water. That's not like a normal metal. They're very soft. You can cut them with a knife. That's not like a normal metal. They have a low melting point, like 60, 70 degrees, but they do conduct electricity. The main thing, though, is they're really reactive, okay? You have to store them under oil to stop them reacting with oxygen. As you can see, their density increasing here, and they get more reactive as you go down the group, and you need to be able to explain why. Lithium fizzes, sodium has an orange flame, and potassium kind of explodes with a lilac flame. They get more reactive. Here are the general equations, and as you can see, hydrogen gas is being produced. And what would you observe? Well, we add some universal indicator to the water, and it'll be green at the start, but when you add your alkali metal, it forms either a hydroxide, potassium hydroxide, sodium hydroxide. Either way, it will turn the universal indicator purple. So your observations, you're going to see fizzing and the color change of the indicator. Sodium, you'll see a yellow flame, and so on. Okay, what are the conclusions? Bubbling and fizzing, it's very reactive. The metals floating on water proves they have a low density, and the metals melt during the reaction proves it has a low melting point. So, why? Why does this happen? Why do they get more reactive as you go down the group? Okay, the whole basis is on how easy they lose that outer electron. Here's lithium becoming a lithium ion. Here's sodium losing 1 electron to become a sodium ion. And I'm going to compare a really small group 1 with a really large group 1, lithium with rubidium. Now, before I talk about this, I need to introduce one concept called electron shielding. It's where the electrons in inner shells block the positive nucleus from the outer shell. So it just makes them feel the nuclear charge less strongly and makes them be lost more easily. They kind of block the nucleus. Now, let's have a quick look here as to why do the alkali metals get more reactive. And this is such a commonly asked question, you really need to know this. 1, the atomic radius increases. That's a fancy way for saying the atoms get bigger. 1, there is more electron shielding. Therefore, the outermost shell feels the nuclear charge less strongly, making it easier to lose the outer electron. Therefore, the reactivity increases. So rubidium will have a much easier time losing that outer electron to become positive. So lithium will have a much harder time because there's less electron shielding and a smaller atomic radius. Now, on to group 7, the halogens. You need to know some things. Firstly, there exist as pairs, F2Cl2, Br2I2, At2. They all are diatomic. They are poisonous, they're toxic. Their colors get darker as you go down the group. Fluorine is pale yellow, yellow-green, and so on. Their melting and boiling points increase as you go down the group, and they get less reactive as well as you go down the group. Now, okay, why does the reactivity decrease as you go down the group? Why? Well, it's actually very similar to why the group 1s increase. All halogens have 7 electrons in their outer shell and need to attract 1 more. Let's take a look at fluorine. Okay, there's not a lot of electron shielding. It's got a small atomic radius, so it will easily hoover up that last electron. Whereas a cation has a load of electron shielding and a large atomic radius, therefore it will find it hard. Here's it actually what you would write in your exam. So just pay attention to this. It's pretty much the same answer for the alkali metals. Point 1 the same. Point 2 the same. Therefore, the outermost shell feels a nuclear charge less strongly, making it harder to attract the final electron. Therefore, the reactivity decreases. That's why they get less reactive. Why do their melting and boiling points increase as you go down the group? As you can see, it goes from minus 220 for fluorine to 114 for iodine. These increase quite strongly. So chlorine is a gas, bromine is a liquid, and iodine is a solid. Well, in order to understand this, you need to know about simple molecular substances, okay? Or the weak intermolecular forces, as we call it. Now, I'm just going to quickly show you what these weak intermolecular forces are. It's not on your course, but it will help you understand what's going on, so I think you should know it. As you can see in this picture, all the atoms are spread out evenly, there's no charge. But this is based on the assumption that they are stationary, that the electrons are not moving. The electrons are moving, and they're moving pretty fast, at 3,000 kilometers a second. Okay, to put that in perspective, that's enough to orbit the planet Earth in 14 seconds. So if it could orbit Earth in 14 seconds, it can certainly orbit a tiny atom very, very quickly, okay? It can do 57,000 trillion orbits a second. That's just insane. To put it in perspective, okay, the Earth has only done 4.5 billion orbits of the Sun. It will do 12,600,000 times that in 1 second. So it's just zooming around. So just for a split second, all the electrons might find themselves on one side of the atom. That would make that part a bit negative. I know it looks like a 6, but it actually means just θ. It's just a partial charge. That leaves the middle part positive and the other side negative as well. That's not symmetrical. And that is the origin of weak intermolecular forces. They only exist for a split second, but in trillions of molecules, and this happening all the time, it does add up to large molecules like iodine and acetylene are solid, even though they only have weak intermolecular forces. So there's covalent bonding inside, but weak intermolecular forces between the molecules. These do not require a lot of energy to overcome, and that's why they're generally gases. So why does the melting and boiling points increase? They have extra electrons, so the intermolecular forces increase. You know why they increase, because if you have more electrons, you're going to have bigger positive and negative charges. Simple as that. Now, so fluorine and chlorine are gases, bromine is a liquid, and iodine and acetylene are solids. Next, you need to know about displacement reactions. A displacement reaction is when a more reactive substance displaces a less reactive substance from a compound. So A is clearly more reactive than B, so it displaces B and joins C. That's a simple version of it. Now, as regards to halogens, chlorine is above bromine in the periodic table, so it is more reactive. So chlorine will displace bromine from the compound, as you can see here, to form potassium chloride. And the bromine will just be an orange liquid. What will you observe? The solution turning orange. Chlorine will displace iodine again because it's above it, and bromine will displace iodine again because it's above it. You might have paused and let's have a quick look at them there. Now, and here's some pictures. So chlorine, not too much color. Bromine's kind of orange, and I like and probably go for purple for iodine. Now, ionic equations. This is really higher level only, okay? So if you're doing foundation level, don't worry about this. So a chemical equation shows the movement of atoms. An ionic equation shows the actual movement of electrons in a chemical reaction. How? Because it shows us the charges. I know if an atom has a charge of +2, it's lost 2 electrons. I know if an atom has becomes an ion with a charge of -2, it has gained 2 electrons. So chemistry is all about electrons. The protons and neutrons are buried deep in the nucleus. So showing the actual movement of electrons gives us more information and makes us better chemists. So here's the chemical equation. This tells me that magnesium joins with iodine to form magnesium iodide, but the ionic equation shows me that magnesium has lost 2 electrons and every iodine has gained 1 electron each. It gives me more information. Oil rig is how you are remembered. Oxidation is the loss of electrons, reduction is the gain, and these always happen at the same time in what we call redox reactions. I've included a picture of an oil rig because I realized a lot of kids don't actually know what an oil rig is. So there's a picture of one just so you know. So a redox reaction, they always happen at the same time. A has lost electrons, it becomes positive. B has gained electrons, it's oxidized, it becomes negative. You can show this by half equations. Half equations are used to show the movement of electrons and what has been oxidized and what has been reduced. So I'm going to show you the half equations here for what we've been talking about, magnesium and iodine to form magnesium iodide. Sorry, I wrote magnesium oxide there, I should have wrote iodide. Okay, the magnesium has lost 2 electrons, we say it has been oxidized, and the iodine has gained those 2 electrons to form 2 iodide ions, we say it has been reduced. So that's the overall ionic equation. So displacement reactions on ionic equations, you need to be able to talk this, and here's where your play pause button will come in quite handy. So what does an oxidation state mean? It means the charge on an ion in a compound. By definition, the oxidation state of any element is 0, and no matter what, the oxidation state of oxygen is O2-. That will actually come in pretty handy. So here's the ionic equations for chlorine displacing iodine as it's more reactive. The chlorine is gaining reluctance, it's reduced, the iodine is oxidized. Now press play and pause on these just to make sure you understand what's going on. And the overall ionic equation is this as follows. The chlorine is reduced, the bromine is oxidized, and nothing happens to the sodium. You can see it's +1 on the reactant and product side, so you ignore it. The overall ionic equation is that. Next, here's another example with fluorine displacing oxygen. Okay, now as you can see again, nothing happens to the sodium, so we ignore that. And here's the overall ionic equation. Now you might want to rewind this a couple of times to make sure you see where the charges come from. Now on to group 0, the noble gases. Okay, the noble gases, they don't react with anything. Why? Because they all have a full outer shell. Okay, they're happiest when they're left alone. They are monatomic, they exist on their own because they have a full outer shell. They are colorless. Their melting and boiling points increase as you go down the group. Again, more electrons, stronger, weaker intermolecular forces, and they are inert or unreactive as they have full outer shells. Because they weren't discovered until very recently, really, because we just didn't know they were there. So their trends and boiling points increase. Okay, radon will have a higher melting boiling point simply because it's got stronger, weak intermolecular forces. That's it. More electrons, more stronger, weak intermolecular forces. And finally, the transition metals. The transition metals, okay, they are that block in the middle. They can either form, they're normal metals, what you think of as a normal metal, okay, like door handles. And they're good conductors of heat and electricity. They're dense, they're strong, they're shiny. Okay, here's some very common metals here. And transition metal ions, they tend to form colored ions with charges, and it can be 2+ or 3+. That's why you can't put them into groups. They're very often used as catalysts. Catalysts speed up chemical reactions by lowering the activation energy. That's more kind of topic 5 though, So we'll talk about that a bit later, topic 5 and topic 6. And you need to be able to compare the alkali metals, okay, with the transition metals, okay? Okay, they are much less reactive than the alkali metals. They don't go on fire or explode. They have a much, alkali metals have a much lower density, okay? That they float on water, transition metals will sink. And they have much higher melting points, okay? So therefore, the group 1 metals will melt in water, whereas look at how high, 1538 degrees for iron, much higher, whereas potassium melts at 63 degrees. And on to the final part of the periodic table, which is the non-metals, that's your sulfur and your red phosphorus and so on, okay? They tend to be dull, low melting and boiling points. They don't conduct electricity as they don't have delocalized electrons. And that is the periodic table done. Now, on to topic 2, structure and bonding, okay? So, we're going to talk about ionic bonding, covalent bonding, and metallic bonding. Trust me, this topic is way quicker than the previous one. We'll fly through this and then we're done. So here's the periodic table of the elements. Why do atoms react at all? Again, all atoms will gain, lose, or share electrons to have a full outer shell. When I'm talking about ions, I'm talking about gaining or losing. So what are ions? They don't have the same number of protons and electrons, so they have a charge. Metals tend to lose electrons and become positive. Non-metals tend to gain electrons and become negative. Ha ha ha. So an atom has a charge of 0, but here's lithium losing an electron. It now has a charge of +1. It is now an ion. Here's sodium losing its outer shell electron to become an ion. Here's chlorine gaining an electron to become an anion, a negative ion. Aluminium's in group 3. It loses its outer 3 to have a charge of +3. And here's some other examples. Now, here's the key point with ionic bonding, okay? Opposite charges attract each other. There's electrostatic attraction. So in general, a metal gives an electron to a non-metal, becoming positive and negative, and they attract each other. That's what ionic bonding is. So we're going to have a look here now at predicting ionic formula. Okay, and you need to know about ratios. Here is a plus 1-to-1 ratio, 1 plus charge, 1 minus. Here the needs 2 chlorines, so that's MgCl2, and aluminium will need 3 chlorines to balance out the 3 plus charges, AlCl3. Here 2 sodiums are needed to balance the 2 minus and the oxygen, so that's Na2O. Here's a 1-to-1 ratio. You can pause and play as we go through these. You can also have compound anions like the hydroxide ion, that's OH minus, you need to know that one. Sulfate, yeah, that's another one. And sodium hydroxide, you just treat them as one unit, but the key is to put them into brackets, okay? Here the calcium needs 2 hydroxide ions, you put the hydroxide in brackets. And the hardest one you could probably be asked would be aluminium sulfate, where it's a 2-to-3 ratio, so you have to double to make up 2 times 3 is 6 and 3 times 2 is 6 to get the balance right. So you need to be able to draw and write about ionic bonding. That is where dot cross diagrams come in, okay? Dot cross diagrams are solely because you can only write in black and ink in your exam. So you need to use dots and crosses to show where the electrons come from because you can't use color. So draw a dot cross diagram of the bonding in sodium chloride. Well, here's the outer shell electron being moved, but your exam answer is just what I've highlighted in red. That's all you have to do. You need to describe it in words for 4 marks. Sodium is in group 1. It has 1 electron in its outer shell. Chlorine is in group 7. It has 7 electrons in its outer shell. Every sodium atom gives 1 electron to every chlorine atom, forming Na plus ions and Cl minus ions. And finally, the oppositely charged ions then join together in an ionic bond due to their electrostatic attraction. You need to learn that off by heart. And here's some other examples now. This is your exam answer. Now I just pause, read through this. It's the same answer every time. 1-to-1 ratio, same answer. Play and pause, play and pause. They love aluminium oxide. It's the hardest one you can be asked. 2 aluminium atoms give 3 electrons each to 3 oxygen atoms, forming Al3 plus ions and O2 minus ions. Now, we're nearly finished. We're nearly there. We're on to giant ionic structures, a giant ionic lattice, okay? Giant. You mightn't consider it giant, a tiny grain of salt, but in a tiny grain of salt, there's 600 million trillion ions in one tiny grain of salt. That's giant, okay? Here, if you pause for a second to give you a kind of scale of the number, it's just huge. Okay, we can't even get our head around it, but it is a giant compound. So describe the structure and bonding in salt. It has a regular structure called a giant ionic lattice. Every Na plus ion is surrounded by 6 Cl minus ions, and every Cl minus ion is surrounded by 6 Na plus ions. This is because we live in a 3D universe. The oppositely charged ions are joined together in an ionic bond due to their electrostatic attraction. Now, sometimes you see this ball and stick model and they ask for limitations. Okay, in reality, the ions are touching, they don't have lines between them, and it gives the impression that the bonds just act in one direction when they act in 3D throughout the entire lattice. Explain the properties of ionic compounds. They're solids at room temperatures. That means they have a high melting and boiling point. That's because ionic bonds are strong and they require a large amount of energy to overcome. Please remember that phrase. That's the phrase you have to use in your exam. They take a large amount of energy to overcome. Do they conduct electricity? When they're solid, they don't conduct electricity because the ions are not free to move. If you melt them, they do conduct electricity because the ions will be free to move, or dissolve them in water. Either way, they will conduct electricity. You'll see this when you talk about electrolysis later on. So you want to play and pause, make sure you can answer these questions. Again, same 4-mark answer. Part D, titanium chloride is a liquid. Why would you not expect it? Well, it's an ionic compound and it should have strong electrostatic attraction, so it should be a solid. There's the final 4 marks for that dot cross diagram there. That's easy marks if you ask me. Now we're on to covalent bonding. Covalent bonding is the shared part. Atoms will gain, lose, or share electrons to have a full outer shell. So a covalent bond, if you're asked to define it, is a shared pair of electrons and it is between non-metals. Here's hydrogen. Here's chlorine. You have to be able to draw all of these. Maybe pause to make sure you can soak it in. Oxygen's got a double bond, so 2 dot crosses. And nitrogen's got a treble bond, so 3 dot crosses in the middle. It just has to add up to 8 in the Venn diagram. You also have to draw a more complicated substance. Here's methane. They love asking this next one, ammonia, because it's the case study in our course, the Haber process. And water as well. So here's a typical exam question. A limitation of dot cross diagrams that it only shows the 2D shape, not the 3D shape of the molecule. And here's one that you're asked to fill out as well. Just pause and have a look, see, make sure you understand them. Now, giant covalent lattice. They love comparing diamond with graphite, okay? Here's the order of bond strength: covalent, ionic, metallic, and then weak intermolecular forces. So giant covalent structures. So allotropes, and we really talk about allotropes of carbon. They have the same chemical formula, but a different structural formula. Picture it like bricks. I can make bricks of Lego. I can make different shaped things with them, but the bricks are the same. So I'm going to focus on graphite and diamond quickly, and then we'll do the other allotropes really quickly. So diamond is the hardest substance known to man. It has a tetrahedral structure where every carbon atom is covalently bonded to 4 others. Property 1, it is the hardest substance known to man. Every carbon atom is covalently bonded to 4 others, making it very strong. It has a very high melting point and boiling point. Again, it's the same answer. Every carbon atom is covalently bonded, and these require a lot of energy to overcome. And then property 3, it does not conduct electricity. Carbon has 4 electrons in its outer shell. Every carbon atom is covalently bonded to 4 others, so therefore there are no delocalized electrons which can travel through the layers carrying a charge. So, here's a typical exam question. There you go. Giant covalent lattice. Now let's talk about graphite. Graphite's kind of the opposite, okay? It's soft and it does conduct electricity. Here's why. In graphite, every carbon atom is only covalently bonded to 3 others, and that makes it form layers with only weak intermolecular forces between the layers. These layers can slide over each other, making it soft. So just pause that and read, make sure you understand why it's soft. Why it still has a very high melting and boiling point because it's covalently bonded to 3 other carbon atoms and it requires a lot of energy to overcome. But it does conduct electricity. Why? Because there are delocalized electrons which can travel through the structure carrying the charge. I've underlined these in red because that's what you must write in your exam. Typical exam question. Carbon, why is graphite soft? The layers can slide over each other because there are only weak intermolecular forces between the layers. Diamond is very hard. Why is diamond very hard? Well, every covalent bonds are very strong, and it's got 4 between each of them. Why does graphite conduct electricity? It has delocalized electrons which can move through the whole structure carrying the charge. Here are just other allotropes of carbon briefly. Graphene is just one layer of graphite, just one layer. Again, it will conduct electricity and it will have a high melting point. Fullerenes kind of look like these footballs and they have many uses, okay? They are, and here's some nanotubes which are fullerenes wrapped around, okay? So uses of fullerenes, okay, they can be used for drug delivery, they're used as catalysts, lubricants, strengthening materials, and electronics. You don't really need to know too much about them, but know that nanotubes are kind of like graphite, a layer of graphene wrapped up, so they do conduct electricity. And here's an exam question and the marking scheme for it. And now finally we're nearly finished, we're nearly there, metallic bonding, okay? So here's a load of metals. As you can see, they're all solids. Why are they solid? There must be some strong forces. In metallic bonding, there is electrostatic attraction between the positive metal ions and the negative delocalized electrons. That's what metallic bonding is. Okay, as you can see, as the charge of the ion increases, so does the melting and boiling point as you go across the group. Here's why. Sodium only has a charge of +1, whereas aluminium ions form 3 pluses. That means there will be a stronger electrostatic attraction and a much higher melting and boiling point. So here are some, just I'm going to pause this to read the exact answer. That's just what I said. But the key phrase is at the bottom, more energy will be needed to overcome. Here's a giant metallic lattice. Here's a picture of it. And the physical properties of metals. Metals are strong and malleable. They can be bent to shape. We saw that with the gold leaf experiment earlier on. They're great at conducting heat and electricity. Why? Because they have delocalized electrons which can travel through the layers conducting the heat and electricity. And they generally have high melting and boiling points due to the strong electrostatic attraction between the positive metal ions and the delocalized electrons. They're also ductile, thus out of interest they can be stretched into wires. Improving the properties of metals, well, pure metals tend to be soft, whereas an alloy is a mixture of a metal with a different substance. Okay, in a pure metal, all the atoms are the same size. This means the layers can slide over each other, making it weak. In an alloy, some of the atoms are different sizes. This means the layers cannot slide over each other, making it strong. And as you can see that visually there. Here an example of some alloys. Bronze is copper and tin. Brass is copper and zinc. You do need to know those for your course. And so here are your giant covalent structure, giant ionic, giant metallic. They're all solids with high melting points. If it's a gas, there's only weak intermolecular forces between them. So press pause here for a moment to know why they're solids. They have giant lattice structures. And then finally, we're on to simple molecular substances, okay? Now, I've already told you about the origin of the weak intermolecular forces, even though it's not on your course. You can just go back and see that. But basically, they don't have a structure. Gases don't have a structure because there's only weak intermolecular forces between the molecules. So intra means inside. Inside the molecules, there's strong covalent bonds. But between the molecules, there's only weak intermolecular forces. Here's a typical exam question. Dot cross diagram of nitrogen. And why is nitrogen a gas? Because there's only weak intermolecular forces that require a little energy to overcome. So that is it. We've got there in an hour, just in an hour, okay? Topic 1 and topic 2 done, structure and bonding. Now we're just nearly there with the states of matter. This will only take 2 minutes and we're done, okay? Changing states, this is also in physics, okay? Solid changing to a liquid, changing to a gas. You know all of this, okay? You know your state symbols. How can you tell that this reaction is done at a high temperature? Well, because the magnesium is a gas, okay? Magnesium should be very high temperature for it to be a gas. And finally, this is not on combined, it is on triple only, but the main thing is surface area to volume ratio. So I would actually continue this even if you are doing combined science, because the maths is important. It comes up in biology, chemistry and physics, this question, surface area to volume ratio. So it's going to be on one of your papers. So nanoparticles are very small, just a few hundred or a few thousand atoms, okay? And here's how you find the volume of a cube. You just multiply the area, you cube it. And the surface area of the cube, well, you find the area of one side, and a cube has 6 sides. So you just multiply the area by 6. And basically having a large surface area to volume ratio is good because you can expose what's deep inside. As you can see, as a molecule gets bigger, its surface area to volume ratio decreases from 6 to 1 to 3 to 1 to 2 to 1. So the smaller the particle, the larger its surface area to volume ratio, the more useful it can be. Basically, stuff just isn't buried inside and not doing anything. So surface area is pretty important, okay? It increases the surface area. This is more rates of reaction. But they're very good at catalysts, okay? Because they have a large surface area, they're very useful as catalysts. What's the point? It's basically if you increase the surface area, you will increase, rather than all the stuff being buried inside, it will be more financially viable and you'll make more money and profit. And that's what business is all about. Here are some uses of nanoparticles. You can read them quickly. And for example, invisible sunscreen. Nanoparticles are smaller than the wavelength of light, so they're invisible in visible light, but they're not shorter than the wavelength of UV light, so they still stop you getting sunburn. Also, because you use less, it saves money. Okay, so you can read that quickly. And finally, to play and pause on some exam questions on nanotech, and then we're done. Calculate the surface area of this cube. Well, 6 times 2.8 squared, 47 when I round it to 2 significant figures. Surface area to volume ratio, make sure you can do this calculation. 6 to 1. How does the size of a nanoparticle? A few hundred atoms or allow a few thousand, and they have a larger surface area, so they're a better catalyst. So that's it, we're done. We finally got there. Topic 1 and 2, part done. So that is the foundations, And now you're going to tune into the next video where I'll do topic 3, 4, and 5, and then finish off with some really good exam practice. So thanks for staying with me, and I'll chat to you soon again, okay? So all the best. Cheers. Thank you.